Hello, good afternoon. So it's such a honor to be here among this amazing crew of creative technologists, designers. So yeah, we're a small team. We are 4 people actually, with very different interests. We come from fields like graphic design, computer science, architecture, music as well. So we all love music, or we play instruments. And our projects always have this component. So we do like a very deep research on audiovisual language. We love these tight relationships between the sonic and the visual. And we build software tools that allow us to go that deep into these relationships. Anyhow, our projects are eclectic because we have many interests. Most of the work we do is kind of artistic, to say so. We do commissions for brands, but not that much, just the minimum to pay for the bills. So we love experimenting and being free, kind of, or come out with our own paranoias. So this cloud of concepts, or this cloud of methods, working with design, or working with perception, and blending it together into architectural spaces, doing it ourselves, either it's software or hardware, working with maths, and blending it with software engineering. All this is always present in our works. And in fact, what I'm gonna tell today is this journey we've been doing from screen to space. We come from a very underground scene in Barcelona, the end of the 90s, beginning of 2000s. We come actually from the BJ, the video jockey field, and the electronic music field, all the rave movement and so on. So we began there. And for many years, we worked as BJs on parties or nightclubs. But somehow, we got full of not having attention from the audience. So you can imagine what the audience was in a nightclub. No one gave a fuck about what the BJ was doing. They were just partying, dancing, drinking, and they didn't matter if you were like working with super cool motion graphics or you were elaborating a real-time discourse. So that was like our VJ crisis, or we called it like the VJ crisis. And we tried to move on to new ways of exploring audiovisual language out of the night somehow. And that's where our journey from screen to space started. One of the first projects that we did on this, or the first stops on this trip, was an installation which was called VJ Yourself, which was some kind of a reinterpretation of a magic mirror, but using digital technologies. This was an interactive installation based on lots of audio or electronic music concepts, but ported into real-time video. And you could stand in front of a camera, and there was a screen that was showing your image, but your image like 3 seconds before, 4 seconds before, and in that way you could like create choreographies with yourself. This happened in 2006, and recently we updated that project, and we made a new version, and nowadays this is we are showing this again in music festivals or museums or wherever they call us. This is a little snippet of this work. I'm gonna be talking on top of the video. So you see there's this guy, there's a camera on here, and there's this image of himself a little bit in the past, like some seconds in the past or some milliseconds in the past. Actually, there's many ways of accessing this buffer of images that we stored in memory. And on these examples, what we do is like we access multiple copies of the image, but delayed some milliseconds in the past. So you can simultaneously see your real-time image blended with yourself 200 milliseconds ago, 400 milliseconds ago, 600 milliseconds ago, and so on. At the same time, there's many like topological modifications we can do on the image. So it's not just about temporal modification or temporal mirroring of the image, but also like position, scale, rotation of the of this real-time video feed. And mostly through waveforms, we'll go about, or I'll go deeper about this whole waveform methodology for controlling stuff later on the conference. But you can tell, you can see, there appear these waves of time and space on these images, and this is because there's on the underlying processes there's these wave functions, like here, controlling the whole thing. This was our first step, like trying to get out of the screen and integrating interactivity and human interaction in the whole equation. On this journey outside the square boundaries of screens or traditional screens, we've been finding different approaches and different kinds of projects. This is something that we've been doing recently. It's a very simple but very funny thing to do. This is a processing software or a little application we did to create generative graphics to be printed, which are controlled through all these probabilities. So everything is based on a regular grid. You see that always the drawings are divided into these grids of squares. And inside each of the cells of this picture, you can define the probability of a circle being painted, or a triangle, or horizontal lines, or diagonal lines, or little points, or whatever, actually. And with this very simple probability control, you can come up with very nice drawings. Actually, there's this hallucination mode, which is just randomizing the different probability parameters, that is creating this. These last drawings you've seen were just like the product of this randomization of parameters, which is very useful when you are not inspired. You just press the random button, everything gets randomized, and maybe you get nice ideas that you wouldn't arrive by your own intuition or by your own sliding. At the end, this is finally being plotted, or we did this to create these plotted graphics. This is the outcome of the software is a vectorial or like a SVG file that you can plot with these AxiDraw plotters or these pen plotters with colors or whatever. And these are like the different results coming out from this software. So different densities of grids or different, by adjusting the different probabilities, you can come up with different drawings. This is very fun to do. Obviously, this is not giving us any money. We do this for fun. We do this for exploring, for learning. And maybe these things we learn, we can apply them on a different project that maybe is more profitable. But we love doing these things, and we don't want to stop doing this kind of stuff. So you see, this is a very versatile tool. Okay, it's always greedy. But it's nice. Going on with that idea of moving from the screen or moving beyond the screen, at some point we discovered projection mapping. We were with a collective in Barcelona called Telenoica. We were like from 2009 to 2012 doing many international projection mapping projects. But at some point we got full of the medium, or we We felt like the exploration was already done, and we were kind of full of this cliché, like collapsing buildings, flying dragons, and strokes, and so on. And we were wondering if it was possible to make something meaningful with projection mapping out of these shows or this spectacularity. And luckily, we got a commission from the Heritage Department of the Catalan government to restitute a Romanesque painting from the 12th century using light or using projection mapping instead of using chemical pigments. It wasn't done ever before, so it required a lot of research or technical research to see if it was really possible. And the whole story is that this is the place where this restitution had to be done was in this church, which is high in the mountains in the Pyrenees. The original painting was taken off in the 50s and brought to Barcelona. And on its original place, there was, or they put a copy, like a chemical copy with pigments. Actually, what you see there is the copy that there was there. And obviously, the first thing to be done was to remove that copy and arrive to this state. And we were lucky that when they removed this copy that was put there on the 50s, there appeared these deep layers of the painting, of the original 12th century paintings. So we had something, or we had these shadows of the reality. So our work was to fulfill this space with image and to make the projection to match exactly what these deep layers of the painting. This is some tech porn, like where the projectors are placed and like the adjustment chart on the apse of the church. We did some 3D scanning of the, with a laser scanner of the church to have like the exact geometry. We use Cinema 4D, blah blah blah, to map the image on the church geometry. This is the deep layers of the, it's a close-up of the deep layers, and this is actually a photography of the projection mapping, matching this space. Nowadays, what you find, this is a permanent installation. Nowadays, what you find in the Pyrenees, if you go to see this project, it's actually these 3 states of the painting. What you see there is what's there for sure, or what you see there if there's no electricity that day. What you see in the middle is the projection of the painting that was conserved in Barcelona, so what was kept of this painting. And this is a hypothesis of how this could have looked on the 12th century. There was a little bit of discussion with the historians, with the architects, with the experts to arrive to an agreement whether we had or not to invent or to illustrate these figures or these characters. There was many people that had the opinion that this had to be just silhouettes. But our position was that because this is not harming the real thing, it's light just on the visible spectrum, and because video at the end is a very flexible medium. If you don't like it, we can remove it. But let's try to do this figurative hypothesis. So if you go there, you can find any of these 3 states. And in fact, when there's like a big group standing on this church museum, there starts like an animation which shows a little bit of the pictorial process, like starting from the sketches, then like the color fields, and so on. We can see a little bit of this animation. To be sincere, we never thought we were gonna map Jesus Christ. But it was funny, it was kind of transcendental. stuff, so we couldn't have many like 3D effects or whatever, which was our intention actually. And now here comes the part I like the most. You will see this white ball moving actually reveals what's for real on that space. So you can see, like the deep layers on top or below the projected image. It's such a simple resource, but it works really well to understand how this is working. So. Okay, so now we felt that we made a little step on this trip from screen to space, but at the end, projection mapping is nothing more than projecting on a surface. So we're not really colonizing spaces, but we are colonizing surfaces. So we try to figure out how could we achieve this space colonization. It sounds kind of sci-fi. And that's when we discovered light. So we were like pixel guys, or we were working mainly with image on screen. But we discovered LEDs, we discovered lighting fixtures, and we started working on that kind of projects and seeing that this could be a super cool weapon or tool to colonize the space or the architectural space to create immersive installations. One of our first projects was this installation inside an old airplane. This was called Stargate. It was people was coming inside here, and there was like this abstract animation recreating like entering a wormhole or flying in a spaceship. And at the end, we were using these LED strips, pixel controlled. Maybe some of you know, there's this pixel mapping technique that allows you to map a pixel on a video image to a LED diode on an LED strip. So using that technique, we came up with this funny project. So something that was interesting on this project that is difficult to understand was like audio spatialization. When a light comes to you, sound is also coming to you. There was like 4 speakers on each side of the plane. So when a comet is coming near you, you can hear it approaching. This was 2014, and from that moment on, poor Francisco. From that moment on, we started working, using these kind of tools, like applying what we learned on the digital image domain into the light domain using this metaphor of pixel mapping or LED to pixel. This was a recent project that happened some months ago. This was in the Copenhagen Opera. We were commissioned by this guy, Francisco Negrin, who was the stage director, to collaborate with the set designer to embed light into the set design. So having image not as a separated thing from the stage or from the set, but as another ingredient of the set design itself. So what we did was to embed, again, LED strips on the wood wall, on the different constructions, and we came up with this kind of light sculptures, which are a blend of iron, wood, and pixels, which appear in different moments of the opera and on different configurations, and which allow us to create like emotive moments. all along the plane. So maybe at this point it's nice to make a little insight on how this works. So usually what we do is to create a pixel map, which is this weird thing here, which looks like a glitchy image, but it's not. It's actually a real map or a technical image. Like every color zone represents a different physical zone on the set. Like all the blue, like this blue zone over there are the pixels that are related to this square palace that you could see before. The purple zone is like the LED strips that are on the floor, and so on. And we use this map to create low-resolution video files, which are usually generated using our own software that we render as PNG sequences, and then we process them further in After Effects or whatever. But it's mainly based on generative stuff created on our own software. We'll go around that in a while. So that's how it looks like. So at the end, what you saw on the LEDs on stage is nothing else than a folded screen. Or you can imagine it as a screen with disordered pixels, or with pixels ordered the way you want, not on a square matrix. So that is helping us, or this kind of techniques are helping us to take over the space. Following that idea, again, of colonizing space, how can we, using this pixel LED metaphor, how can we go further with that? This is a project we did some years ago, collaborating with a very good friend of us, with Alex, who is a very skilled electronic engineer. We felt that it would be super cool to have floating pixels. And what we decided was to use like helium balloons with an LED inside, so that we could raise these balloons on the air and create this kind of architectures, or these floating architectures. All the electronics is done by us, or is designed and built by us. It features like a wireless LED receiver, or a wireless radio receiver to control the color of the LEDs. It's powered with batteries, so there's no wires involved. And it's kind of lightweight, so that the helium balloon, with the power of the helium inside each of the balloons, all these electronics can be raised. That's how more or less the electronics look. That's at the end. We just have a little bunch of them. We have 81 to create like a 9x9 matrix. And at the end, what you've seen wasn't anything else than a very low resolution screen. It was a 9x9 pixels screen, but the pixels were not this tiny thing on your screen, but were helium balloons. And with the ability to move them or to raise them, like using strings and creating these dynamic architectures. So with these tools, and with some other tools that we'll add after a while, we are starting to take over space. But at some point, we felt that we needed kind of a parallel process in music. So if we are going out of the flat squares, or the square boundary of traditional screens, we want to do the same in music. So we want to get out of the flat surfaces of stereo image. We want to get out, if possible, of speakers, and start working with different methodologies. And how do we approach that, or how can we do that? And this is going to be a little bit weird for the next slides. We started working with algorithmic music. And one of the first things that we found was this kind of charts, because we were doing some research on how can we do meaningful music or beautiful music by modeling, mathematically modeling processes. So we found this kind of charts. These are kind of navigation charts for musicians. So if you are in the sixth chord, you can move to the fourth major chord, and if you're in the fourth major chord, you can move to the third minor chord, and so on. And this serves as a guide for improvisation for musicians. We found many of these charts. So how can we model this, and how can we use this to make something beautiful in music? So maths came to the rescue. We found something called, inside probability theory, called Markov chains, which are probability chains. And this image explains it really well. If you're in the A state, you have 40% probabilities of going to E, or you have 60% probabilities of coming back to A. And if you're in E, you have 30% probabilities of going back to E, or 70% probabilities of going to A. So we modeled that into music engines in such a way that we could create like real-time systems that were doing beautiful or meaningful music. An example of this. I strategically positioned this to the bottom so that I can go pointing. So you see there are like these 7 stages. On the first stage, we have like a C major 7th chord. Second stage, we have a C dominant 7th chord, F major 7th, F minor 7th, G 7th, and so on. And you see this red horizontal bar is jumping from one place to the other based on the probabilities that we've defined here at the bottom. So if you're in 1, you can jump to 2 or 7. Let's see what happens. It jumped to 7. If you're in 7, you can jump to 6. It will jump to 6. Now you can just go to 5. You'll go to 5, and then you can go to 1 or 2. So maybe if we can rise music a little bit. This is kind of cheesy. Just for testing purposes. Okay, so this was one of the steps on this algorithmic music thing. This allowed us to create real-time music systems, and it also allowed us to create music that then could be sedimented into a score. We'll see that. This is a different approach, also based on probabilities, but not just for harmony, but also for rhythm. So this was part of a preparation for a string quartet concert. So here we have, first is violin, second is viola, cello, and bass. And just gonna let it play. Kind of creepy, I know. The cool thing of all these algorithms is that they can be turned into something written that a human being can play, more or less. Obviously, you need to make some processing. Humans cannot play maybe that fast, or maybe not on that range of notes or whatever. You need to process a little bit the scores, but you can end with a playable score that humans can read and can play. So all this turned into a very nice project, working with lights and with a live string quartet and with electronic music as well, that happened last year. Maybe we can dim the lights for this one. Okay, so thank you. So a parallel process. So we're trying to get out of the screen, but we're also trying to get out of the speakers. But hey, you've seen like some cool lights moving on there. What's happening with that? No, we haven't seen anything about it. So I already told you a little bit about wave functions, about oscillation. So basically, to control that lights and to design how they behave on time, we create our own software, which is based on low-frequency oscillators, which is a concept that comes from the electronic music field. This is a very primitive version of this software. This was coded in Max MSP, but the principles are the same. I will show you a more modern version of this, but this one is nice because you can see the simulator on there. And this explains a lot of our process. So obviously, we don't own a cathedral, we don't own these lights, but we need somehow to create these projects in the studio. So what we do is that we virtualize the spaces so that we can work with these 3D environments to understand more or less how it will look like in the end. So you see all these wave functions being applied to the movement of motors of lights. And the cool thing happening here is that the same data that feels, that controls it, is also controlling sound. So this turns this into an audiovisual instrument. So we are not doing music on one side and lights on the other side. Everything is just one matter, or everything is just the same source. And that's what we are searching for, or that's what we, at the end, the creation of this kind of language is what we are interested in the first place, no? Creating a unified audiovisual language. And we used many strategies for that. But, no, again, an example of using these waveforms to control lights. This was a weird installation we did somewhere in the US. It was a 100-meter long alley. There was 32 speakers. So when a light is coming to you, the sound is coming to you as well. So there's exact positioning of light and sound. Okay, so I'm gonna go, in the 10 minutes I have left, I'm gonna try to go in deeply into two different projects. I will have to discard one. This is a space in Barcelona where a festival is held, like a visual arts festival is held. We received a commission from this festival to create an installation here. And first thing that we do when we receive such a commission like that for a site-specific project, what we do is to make like an architectural analysis or a geometric analysis of the space. And we come up with this kind of esoteric drawings, like trying to find relationships, distances, or whatever. And this is very nice because it lets us to understand how geometrically the space is behaving and what are the possible, or the interesting relationships that appear there. And actually what we do after that is we usually create some kind of script. So this is how our scripts usually look like. we are super abstract, or we rarely do narrative things, although from time to time we do some narrative stuff. But usually we make that kind of abstract things, defining how we want things to move, like these arrows there, like, don't know, we want to work with directional movements, or we want to work with circular movement, or we want to work with randomness, or whatever. So usually our scripts look like that. And this is some photographies of how this looks like when we apply this to space. This was in the United States, in Day for Night Festival, a really cool festival that actually it's not happening anymore. And we come back to oscillation again, because it's important on this project. So this is a low-frequency oscillator. This is a sinusoidal oscillator controlling a slider. But this is a single oscillator. If we have a bunch of oscillators, if we have a bank of oscillators, actually, and we use each of the oscillators to control the luminance of a pixel, which is these squares. Try to imagine, this is a pixel, these little squares below the sliders. We can create video textures. And if we have millions of these oscillators, we can create big textures. And this is the new version of this oscillation software. Obviously, with MaxMSP, we found like a barrier at some point in terms of performance. And we decided to move to C++ and to create our own MaxMSP, or to create our own touch designer. So we created this nodal environment to work with waves. So what you see here are different presets, and each preset like loads a different state of the modules. And this state of the modules creates a video texture, which is applied on the columns. So this is our simulation made in Unity that makes us understand, or helps us understand, how everything is going to look like on the real place. Because we're audiovisual maniacs, we came up with a sonification methodology based on video textures. So we are doing the opposite way. So instead of making images out of music, we are doing music out of images. So what we do is that we analyze the luminance of pixels in a column, and we apply or we map luminance to volume. So here you have a scheme. So if the pixel like below in the column is lit, there's going to be a 60 hertz oscillation that is going to be heard, more or less, depending on the luminance of that pixel. And that goes up to 9,000 hertz, more or less. And this is the sonification engine in action. It's a little bit creepy, too. But it's just a demonstration of how the whole system works. So this synthesizer is receiving the video texture, and it's being sonified into different ways. And it's very cool because if you're lazy composing music, it makes everything faster. You just need to receive video textures, and there's some music already done there for you, because there's not these dynamics of the image are turned into sound. Let's go fast. This is tech porn. We don't need to go over that. We can look a little bit the video. Oh shit, 5 minutes. I would be here for hours. Hello, creepy alien audiovisual stuff. Thank you, guys. I'm gonna jump this one. This is a cool laser solid light sculpture. I'm gonna jump this one. So let's go see. Final one. So this was a commission by this place, which nowadays is a museum. This was like actually the first big project by Antoni Gaudí, which is a popular or like a very famous Catalan architect. They wanted to attract young people to the museum, or also like locals, not just tourists. And they just gave us the freedom to visit the place and see what we could come up with. And among the different rooms that we could find there, there was this one which had this parabolic dome on there, and which also had this pipe organ. Of course, I wanted to live there, or I want to hack this. I want to play with this. Unfortunately, this organ was restored. It's like a 19th century organ, but it was restored by a young guy who could hack it for us to put like a MIDI card or something that allowed us to play this pipe organ with a computer. We were super happy about that. We spent like many nights working with the music on that place. For those of you who don't know, like a pipe organ, it's like a collection, a massive collection of flutes, actually. So the bigger the flute or the bigger the tube, the lower the sound or the lower pitch. I spent many nights on there. I wanted this instrument or to see what could happen when you plug like 21st century technologies to this kind of old instruments. It was amazing, you will see. And obviously, in parallel, we needed to make some kind of intervention of this architecture. This is a parabolic dome, and it's made of 32 rings of 65 hexagons, so there's an hexagonal tiling on there. Actually, if you make like a schematic drawing of this photography, what you see is this, and in fact, you start seeing some kind of natural patterns inside this whole structure. And we started again making an analysis on the architecture. And we started just connecting dots. If you see these black hexagons on there, are nothing else than these little windows, circular windows on the space. If you connect them, you start to see these petals and these flowers on this space. No? And this is all part of this geometric analysis. We had to come up with a concept, and it was obvious. So what's the concept? We are super abstract, but it was obvious that the concept had to be to make visible what's already there, but you can see with naked eyes. No? So there's all these natural patterns embedded inside the architecture, but are not obvious. So our work was to make that visible and try to find like a parallel way of work. 0 minutes. Okay, I'm going to show you just the final outcome of this work. Okay, so I'm sorry. Thank you very much. Thank you.